Every day we're going to learn one or more new rules of differentiation. So if you have taken physics with Mr. Edlin, you already know one of the rules of differentiation. However, there's like 11 or 12. So you know one, and we're going to get you caught up to speed on all the rest of them. So our goal today is to teach you what is called the power rule. And then I'm also going to teach you how to handle negative integer powers. And then we're going to talk about what it means not only to take one derivative, but what does it mean to take two derivatives, three derivatives, and more, and how those still relate to tangent and normal lines. So that's our goal for today, what you'll walk out of here hopefully having at least an introductory grasp of. All right, so here we go. Let's make sure we all understand a couple things first. If f is a constant function, okay, can you think visually with me? If the function is constant, the function is 11. Okay, that's a constant. What does it look like? All lines are straight. Stop telling me lines are straight. Okay, what kind of a line? Horizontal. Okay, if the function is a constant, then the function is a horizontal line. Okay, it's a plane. It's parallel to the x-axis. It's just all going like this. All right. What's its derivative? If when I say what's its derivative, what you're hearing is, what is its slope?
0.
Okay, 0. So the answer to the derivative for every constant is 0. You don't need Newton for that. You don't need Leibniz for that. You just need common sense to know that the derivative of every constant function is 0. All right, next one. If the function not only has a constant in it, I don't know what I typed there. That should be an X, not a U. Okay, so please fix that in yours. Okay, this is an X. All right, it's right above. It says X and C, so it should be C and X. Okay, so if the function has a constant and an X in it, 5X, negative 3X. Okay, whatever. All right, visually, what does that look like? Okay, an oblique line. Okay, an oblique line. All right, and what is its derivative? And when I say what's its derivative, you are hearing what is its slope?
C.
It's whatever C is. So the derivative of that is C. Okay. You don't need Newton for that. You don't need Leibniz for that either. You never have to do Newton and Leibniz if you are dealing with a line. You only need Newton and Leibniz as soon as we hit curves. Okay, so now we're going to hit curve. Anything with a power is going to be a curved function, whether it's cubic or squared or quartic or quintic, or whether it's a root, a fraction, a rational. Anything with that kind of power is going to be curved. So when I say to you, then what is its derivative, you are hearing from me what is its slope. Okay, and there is a rule, a nice shortcut rule that works for both Newton and Leibniz for these curved things, and this is what it says to do. Take the actual power itself and move it down to the front of x. So what you get instead now is xn. Excuse me, n in front, please. N in front of x. Okay? After you've done that, subtract 1 from the number that x was. So it's dropping it down a power to 1 less. And so this will now have a power that's been lowered by a value of 1. That will always tell you what the derivative is. Okay, also will tell you what the slope is. Okay, so to differentiate, which is a good word, okay, to differentiate is what means to take a derivative is to differentiate. You multiply by n and subtract 1. That works for any curved rational function. Okay, any curved rational function. Hear me that I'm saying rational. I'm not saying trigonometric. I'm not saying logarithmic. I'm not saying, okay, exponential. Any curved rational function. All right, so let's just try it. Here you go. All of these are curved functions, so all of them can use the power rule. So all of them would say, move the power to the front. All right, so f prime becomes, all right, when I move the power to the front, I move 4 to the front, what number do I have in the front now? 20. And I have to follow that with decreasing the power to what number? 3. That is called the derivative. Okay, that will tell you the value of the slope anywhere. Remember, the slope is never the same at any 2 points. The slope is always changing, but that will tell you how to help you figure out what the slope is. All right, will that work on the function g of x? Yes. Why? Okay, because it's a power function. Okay, as long as you can write it as a power, this rule will work, but you have to be able to write it as a power. So again, I move that power value to the front. So g prime becomes 1/2 x, and then the value has to decrease by 1. So what does that bring me to? Negative 1/2. Okay. Now, you can't leave negative exponents. You may leave square roots in the denominator, but you may not leave negative exponents. And so this would need to become a fraction problem. And what would remain in the numerator is the number 1, which is coming from the fraction 1/2. What would be in the denominator is the coefficient of 2, which is also coming from the fraction 1/2. But the x to the 1/2 is going to move and now be the rad x in the denominator. You don't have to rationalize that, though. You may leave radicals in the denominator. Please just don't leave negatives in exponents. All right, will this rule apply to function h? Okay, why? How can I write that? It has to be written as a power. X to the negative 3. Because I can write it as a rational power, then I can find its derivative by moving the power to the front. So the coefficient will be negative 3. And then I have to lower the power down by 1. So what will that give me? To the negative 4th. Okay, and then I don't want to leave that. I would need to make that a fraction. The numerator would be negative 3. The denominator would be x to the 4th. And then that would be the expression of the derivative meaning the slope along that curve. Any questions so far?
How come we can't leave a negative exponent?
You guys always ask me these great questions, and I say, like, hang on for like 3 days. It's just going to make the math. We're going to be doing some cross multiplication, and it's always better to have a denominator when you cross multiply because you got something to cross multiply with. Okay, any other questions on that? Great questions. Okay. This doesn't just work on single terms. Notice that what we just did, f, g, and h, they all were a single term. It was 5x to the 4th. Okay, but it also works on terms that are connected with addition or subtraction. So you can do this to long polynomials, long rational functions that have multiple terms. All right, you just do them piece by piece. So you'll take the derivative separately of the u piece, whatever u happens to be, and then you'll add or subtract to it the derivative of the v piece, whatever v happens to be. And if there was a y piece and a z piece and a w piece, you just, all the pieces you would treat separately from each other. So then an example would be here, how we'd put this all together. Find the tangent line of the curve. Again, notice it says curve, not line. Okay, find the tangent line to the curve of that function at x is 1. All right, well, if that's the function, we should be able to find the f prime for the function. Okay, anybody want to try that? Okay, Evan.
6 times 3 is 18x squared minus 6x.
Okay, does anybody disagree with that? Okay, so we have our derivative. All right, why do we need a derivative? Because we want to find a tangent line, and what 2 things do you need for every tangent line? Point and a slope. So we want to find the point, and we're going to plug 1 into where? Into the original. And we also need a slope, And to find the slope, we're going to plug 1 into where?
F prime.
F to the F prime. Okay, so we have to find a slope and we have to find a point. When we plug 1 into the original, 6x cubed minus 3x squared, and we plug 1 in there, what do we get? A little quick mental math, you're just plugging. Okay, 3. All right, and when we plug 1 into, oops, I forgot 1. Okay, when we plug it into F prime, we're plugging 1 in there, what do we get? 12. All right, and so then we can come up with a tangent line. And our tangent line will be y minus 3 equals 12 x minus 1. And you can leave it like that. If you needed a normal line, you just change the 12 to negative 1/12. You don't have to distribute. You may leave it like that. Okay, here we go. Here's another one. Find an equation for the tangent line to the curve at that following point. All right, so we have a y, but we need a y prime or a dy dx, either one is fine. Okay, in order to find a y prime, we have to rethink of y in a power rational power form. Okay, so let's think a little differently about this. So y is no longer going to be the parabola or the hyperbola 1 over x. Y is going to be what rational function? X to the negative 1, which means y prime is going to be what rational function? Negative 1 x to the, and then I have to lower that, and I lower that and I get negative 2, which gives me 1 negative over x squared. Okay, we already have our point. Our point is already given to be 1, 1. We just need our slope. Our slope would be plugging the value into the derivative instead. So I'm going to plug 1 in there. So negative 1 over 1 squared. So that will give me negative 1. And so then my tangent line is y minus 1, a slope of negative 1, and x minus 1. So then the follow-up question is, once you have the tangent line, what about the normal line? Okay, the normal line is very easy to find. Okay, everything about the tangent line stays the same except for the slope, which changes from negative 1 to positive 1. This is the opposite and the reciprocal, which just became positive 1. How are we doing? Any questions so far? Okay. All right. Now we apply this a little further. Does the curve, oh yeah.
Sorry, can you just
Yep.
Why isn't the slope for the normal line 1 time? I mean, sorry, never mind. That was a stupid question.
Okay, you thought about it and you figured it out while you were saying it. Okay. All right, here's a follow-up question. Does the curve, and I've drawn the curve for you, okay, does the curve have any horizontal tangents? Okay, what I want you to need, I need to make sure you hear is that you're not hearing horizontal asymptotes. A horizontal asymptote is a dotted horizontal imaginary line, which my graph will get really close to but never touch. Okay, clearly this one doesn't have any of those. But this is asking about a horizontal tangent or a horizontal tangent line. Okay, a horizontal tangent line has what kind of slope? Okay, so this is gonna, you could like rephrase the question. If I would say, please rephrase the question. Does this curve have any places where the slope is 0? Okay, so you could change this to, instead of horizontal tangents, you could say places of 0 slope. Okay, that would be another way to say that. Or you could take the word slope out, and what word could you put in instead? Derivative. So you could say, does this curve have any places of 0 derivative? Now visually, they kind of pop out to us places where I would have 0 slope, a place where the slope is for just an instant is perfectly flat. Doesn't last very long, but it happens, okay? So I see one about right here, okay? A place where it's perfectly flat. Doesn't last very long, but it happens right there. We're gonna all guess it's probably at what x value? 0. That's the y value, okay? But we're looking for the x values. Okay, it's also gonna happen down here. Okay, you could guess what the x value was, but if I were to look at my graph, would you guess that it was -2 or? Okay. All right, we'd estimate, but I'm not going to say it's going to be exact. So how many times did this work out to have a 0 derivative? 3. Okay, so to find it, we got to find what the derivative is. All right, so we find our derivative first. Okay, and our derivative, y prime, based on what we were given. So the derivative y prime is move the 4 to the front, and what's the new power on x? 3. Okay, and then what goes in front of the next term? A 16, and the new power on that is x. And then what's the derivative of 2?
0.
0. The derivative of 2 is a constant, and every constant has the derivative of 0. Okay, so we find the derivative. Now we want to set derivative y prime equal to 0. So I'll put my 0 here. Set 0 equal to 4x cubed minus 16x. And then we solve that mathematically. So now we're done with calculus, and it just becomes an algebra problem. Okay, what is the algebra here? Factor out what they have in common. What does it have in common? Besides an x? A 4. Okay, so a 4x, leaving me with x squared. Okay, minus what value? 4, which is difference of squares, which gives me 3 solutions. Okay, a solution for 4x, a solution for x minus 2, a solution for x plus 2. So my solutions are 0, 2, and -2. And so we were estimating that would be about where they were, and that is truly where it worked out. Okay, but don't try that. Don't say, the graph looks like it's 0, 2, and -2, so I'm going to give you that as my answer. You're going to have to back it up with a little calculus and a little algebra. Okay, any questions on that one?
Instead of pulling out the 4x, could you just solve algebraically and just like add the 16x to the other side?
Ooh, okay, I want you to see what happens on that. That's a really good question. Okay, all right, add 16x. Okay, then what?
One of the x's reduces.
So divide by x, divide by x. Okay, 16 equals 4x squared.
And divide
Divide by 4, divide by 4. 4 equals x squared.
plus or minus 4.
Is there any, where's the 0?
Oh, because you can't do
I'm
it.
confused.
You lost the 0 solution. Okay, division leads to losing solutions, okay, as opposed to factoring. There should be, okay, remember your rules here. The number of power that you have is also equal to the number of solutions that you should have. So if your highest power was 3, you should have 3 solutions. So if you do division, you just lost the 0 solution when you divided by x. Because you divided by a variable instead of dividing just by a number. Like the number 4 is fine to divide by the number 4, but you divided by the variable x, which just lost you an answer. Okay. All right, almost done. Okay, now there are multiple kinds of derivatives. We know that the first derivative means the slope. The second derivative is going to have a meaning as well. So is the third derivative. We're not quite ready to learn what those are yet in a physical sense, but the first derivative does mean slope. The way we write that, okay, here is how Leibniz would have written it. The first derivative of y, so dy, with respect to dx. That was Leibniz's way. And then we learned yesterday that Newton would have written it as y prime. but we read it as the first derivative of y with respect to x. This is where Leibniz, these multiple derivatives, where Leibniz starts to be a little bit better. The second derivative is written this way, d2y, okay, over dx, and then the 2 goes after it. There's a long historical reason of why that was. It was because Leibniz's original papers, he was writing it like this. He had d over dx, and he had the y next to it. And so then when he did his second, he kept the y next to it, and he just put his 2's like that. That's why historically it has now become that way. We just now have kind of in our modern writing put the y up there, but it's not wrong to do it either place. Okay, now Newton would do y like this. Okay, now the problem starts to be is that an 11? Is that y11? Is it y1? Like, what is it? Okay, it starts, or is it Roman numerals? Like, it starts to get a little bit different. Okay, the third derivative would be written d3. And then Newton would do this. And then you get to 4. And then all of a sudden Newton changed to literally Roman numerals. And they changed from tick marks to Roman numerals when he got to 4. So Newton started to lose favor with people when he was doing multiple because his notation changed midway. He changed from prime marks to Roman numerals when he got to 4. So Leibniz was preferable because he was consistent and he just used regular numbers. Oh, yeah. That's more common in science than it is in math. Yeah, but I know what you mean. Know what you're talking about. Okay, so if you're asked to find all the derivatives of the polynomial, you think eventually they will run out. So let me show you how many we can do before we run out to nothing. We've used up all of ours. Okay, so let's start with y prime. We'll use Newton. Okay, so what's the first term? So let's have Juliet get us started. Good job. Okay, 4x to the third. Okay, we'll keep going. Jonathan?
4x.
4x. Okay, and then Stephen? Want to try the next part?
Negative 3/4.
Yep, just negative 3/4 because that is just a linear piece, 3/4 x, and so the slope is just the constant 3/4. Okay, and then minus. Okay, and then Kaylin, you want to take the last one? 0, yeah. Okay, do you have to write minus 0? I'll say no, you don't have to write minus 0. Okay, so that's the first derivative. Second derivative. Okay, Alex, you want to get us started?
12x.
To the second. Okay, it's to the second or squared. Okay, SK, keep going. Minus 4, and then another minus 0.
It's plus 4.
Did I copied it wrong. Okay, and then 24x. That's the third. Then we switch to Roman numerals, and it's 24. And after 24, what's it going to be?
0.
And what's it going to be all the time after that? 0 all the way.